Good afternoon, students. So yesterday we had discussed about wave optics. So the important chapter wave optics, that is Huygens principle and the theory of interference, and what is the intensity of the resultant wave and what is the amplitude of the resultant wave, and just some different synopsis. Students, today we are going to discuss about some previous year CET questions. So before going to that, just recall what are the formulas what we are discussed in the last class. So what we are discussed in last class, that is first one is that is theory of interference. Just 5 minutes. What is the important formulas what we are discussed in the last class? First one is theory of interference. Theory of interference. It is y1 equals s sin omega t and y2 equals a sine of omega t plus phi. According to superposition, y equals y1 plus y2. And what is the displacement equation for superposition or resulting wave is, that is r a sine of 2 omega t plus pi by 2. So this is the resulting or displacement equation for superposition principle or superposition waves, where r equals, r means resultant amplitude, r means resultant amplitude. So then most important, what is the resultant amplitude formula? That is 2a cos phi by 2. So keep in mind. So this is the most important formula, r equals 2a cos phi by 2. Next, by using this resultant amplitude, already we know that the last class we have discussed about, we know that r is directly proportional to a square. But amplitude is directly proportional to or intensity. Intensity is directly proportional to a square. The most important formula. So then I direct equals a means 2a cos phi by 2, 2a cos phi by 2 whole square. Then I equals then I equals then I equals 4 a square cos square phi by 2, where I equals 4 a square cos square phi by 2. Then we can write a equals, a means 4 I naught cos square phi by 2. So this is the formula of intensity. This is the formula to calculate intensity of the resulting wave. And next R, this I equals I max, I maximum equals I maximum cos square phi by 2. The most important formula, that is one resultant amplitude formula, and also we have to calculate intensity if two waves of having same amplitude, same wavelength. So note these formulas. And the next one is if two waves having different amplitudes, if two waves having different amplitudes, if two waves having different amplitudes, a1 and a2, what is the resultant wave? That is r equals resultant amplitude can be calculated, then a1 square plus a2 square plus 2 a1 a2 cos phi, a1 a2 cos phi. This is the formula to calculate resultant amplitude of the two waves. If again r square equals a1 square plus a2 square plus 2a1 a2 cos phi, 2a1 a2 cos phi. Already we know that I is directly proportional to what? A square, amplitude square. That is I equals I1 plus I2 plus 2 into square root of I1, I2 cos phi. I1, I2 cos phi. This is the most one of the formula, important formula, and this is also one of the most important formula. So, what is the relation between phase difference and path difference? What is the relation between phase difference? It is delta phi equals 2 pi by lambda into delta x. So, one of the most important formula, delta phi equals 2 pi by lambda into delta x. So, note down all these for most important formula. So, previous year KCET board asked on the basis of these formulas only. Is it clear? And these are all formulas about theory of interference. And the next one is Young's modulus. Young's modulus. Next one is Young's modulus. That is what is the fringe width formula? That is beta equals lambda d divided by d. Fringe width formula beta equals lambda d by d. This is a formula used to calculate fringe width, interference pattern, fringe width, and also bright fringes. Nth bright fringe formula, that is xn equals n lambda d by t. And nth dark fringe, xn equals n2 n minus 1 is 2 n minus 1 lambda d by 2d. So, this is a formula used to calculate nth bright fringe and nth dark fringe. And also, in Young's double slit experiment, so if the any one of the slit, so this is a Young's double slit experiment. So here there are coherent source, they reaching the point P. If any one of the path of the beam, we have to place a transparent sheet like mica of refractive index mu, the entire interference pattern gets shifted. But interference width of the interference pattern does not unaffected. Interference pattern unaffected. That is, we have to calculate a lateral shift. If I place any transparent sheet on the path of this light, the entire interference pattern gets shifted. But width of the interference pattern unaffected, then we have to calculate mu minus 1 t d by d. Ls equals mu minus 1 t d by d, where t is called thickness of the sheet, d capital D is distance between slit and screen, small d is distance between the slits, and mu is refractive index of the sheet. And these are all the important formulas what we had discussed in last class. So now we shall start what are the previous CET questions. And first one is so listen, what are the previous that is in the year 2006. In the year 2006, the first question is light from two coherent sources. Light from two coherent sources of the same amplitude A and wavelength lambda. illuminates the screen. The intensity of the central maximum is I naught. The intensity of a central maximum is I naught. If the source were incoherent, see, if the intensity of the central maximum, if the source are coherent, is I equals 4 I naught. I equals 4 I naught. Sorry, I naught equals I naught equals 4 I. If the sources are more incoherent, the intensity at the same point will is, so if I naught, if the sources are coherent, I naught equals 4I. If the sources are incoherent, that is I equals I naught by 2. Then option 4 is the right answer. Is it clear? So next one, question number 4. In Young's double slit experiment, next one is in Young's double slit experiment. Already you know that what is the formula of Young's double slit experiment. In Young's double slit experiment, with the sodium vapor lap of wavelength, 589 nanometer. So what is the value of nano? That is 10 to the power of minus 9 meter. And the splits width is small d equals 0.58 nanometer. 0.58 nanometer apart the angular width of central maximum. Angular width we have to calculate formula. Angular width of central maximum. So one more formula in Young's double slit experiment, we can calculate the angular width of central maximum. Already you know that always central, always bright fringes formed. So you can calculate the angular width, that is sin theta equals lambda by d. So the formula, right? So sin theta equals lambda by d. We know that the value of lambda is 589 into 10 to the power of minus 9 divided by d, that is 0.589. So option says sin inverse of 0.01, sin inverse of 0.001, 0001, and sin inverse of 0.1. So, but here 589 divided by 0.589, that is we can shift the point, decimal point, 589 into 10 to the power of minus 9. So, 0.589, nothing but this can be written as 589 into 10 to the power of minus 3. Is it clear? So now 589 get cancelled. Then 1 into 10 to the power of minus 9, numerator 10 to the power of plus 3, minus 9 plus 3, 10 to the power of minus 6. Is it clear? See, here 589 10 to the power of minus 9 meter and 0.589 meter. Then minus 9 minus 3, that is minus 6. Is it clear? Then what is the value of d? Thickness 0.580 nanometer and 0.589 millimeter. 0.589 millimeter, this one. So 0.589 millimeter, that is 10 power of minus 3 meter. Or this one is 10 power of minus 3. So minus 3, but minus 6. That is 0.589 into 10 to the power of minus 6 minus 3. 589 into 10 to the power of minus 9 over 589 into 10 to the power of minus 6. So this one get cancelled. That is 1 into 10 to the power of minus 3. 1 into 10 to the power of minus 3. Then sin theta equals 0.001. That is theta equals sin inverse of 0.001. Is it clear? So now option A is sine inverse of 0.001. That is option A is third one. Is it clear? So now, so next one is understood all of you? Next one is in Young's double slit experiment, a third slit is made in between the double slit. In Young's double slit experiment, the third slit made in between the double slit. Then what about interference pattern? What about fringe width? Is it clear? So next one is in Young's double slit experiment, a third slit is made in between the double slit. Then what about, say already we know that this is Young's double slit experiment. A third slit is made in between. A third is in between. What about fringe width? Option A, fringes of unequal width are formed and contrast between the bright and dark fringes is reduced. Intensity of fringes totally disappears. Only bright light is observed on the screen. So option is, if a third slit is made in between the two slits, a contrast between the bright and the dark fringes is reduced. Is it clear? So next, understood? Next one is the direction. Two sources are said to be coherent if they produce waves. In the last class, we have discussed about what is coherent and incoherent sources. What is coherent sources? These are the source which emits a light of constant same wavelength and at constant phase difference. What are incoherent sources? These are the sources which emits light of different phase difference. Here, the different phase difference is the most important word. So, if two waves are said to be coherent, if they produce waves having constant phase difference. If it is incoherent, then the phase difference having a different phase difference. The option is a different phase difference. So here two sources are said to be coherent, then option is having a constant phase difference. Is it clear? Okay, we move on to the next one. Next one. Say question number 8. Say question number 8. Question number 8, that is 2009 KCET question. Young's double slit experiment. See, most of all in KCET in previous what we observed in the previous KCET exams, most of all the questions appears from this Young's double slit experiment. So read carefully the experiment, Young's double slit experiment, and list out all the formulas in Young's double slit experiment, and make some important notes on Young's double slit experiment. It is helpful for all the competitive examination. Say question number 8 in a 2009 KCET examination, Young's double slit experiment gives interference fringe width. Interference fringe width, that is a symbol beta equals 0.3 millimeter. 0.3 millimeter. A thin glass plate made of material of refractive index. See, refractive index 1.5 is kept in the path of light from one of the slits. The fringe width becomes. In the last concept already we have studied in the last class. If any path of the light, we place a thin glass plate made of material, of different of refractive index mu, is kept in the path of the light from one of the slit. Then What is the fringe width becomes? See, already you know that if I place any glass sheet of refractive index mu in the direction of path of light, the interference pattern gets shifted, but interference fringe width becomes unaffected. Fringe width becomes unaffected. That's why here fringe width is 0.3 millimeter. So then, if I place any glass sheet in the path of a light, fringe width unaltered. So answer is 0.3 millimeter only. So option second one, 0.3 millimeter. So keep in mind, if I place any glass sheet, just like mica or any transparent medium in the path of a light, interference pattern gets shifted, but fringe width of interference pattern do not alter. Is it clear? Okay. So next one. Next one. Next one. That is 2010 KCET question. The wavelength of light used in Young's double slit experiment is lambda. Just I will write the formulas of Young's double slit experiment. This is the fringe width formula, that is beta lambda d by d, and bright xn equals n lambda d by d, and for dark xn equals 2 n minus 1 lambda d divided by 2d, and that is a lateral shift. If I place any transparent medium, as we discussed in the last problem, that is mu minus 1 t d divided by small d. So these are the important formulas of Young's double slit experiment. So just observe question number 9. The wavelength of light used in Young's double slit experiment is lambda. Is lambda. The intensity at a point on the screen where the path difference is lambda by 6 is I. Is I. If I naught denotes maximum intensity, then the ratio of I by I and I naught is. See, as already we know that what is the intensity? Formula I equals I naught cos square pi by 2. I equals I naught cos square pi by 2. So first path difference, that is x equals delta x equals lambda, that is a phase difference, that is phase difference, delta phi equals 2 pi by lambda into delta x. So delta phi equals 2 pi by lambda into delta x, means delta x is first here lambda, then lambda lambda get cancelled. Delta phi equals 2 pi. Delta phi equals 2 pi, or it is formula is I equals I naught cos square phi by 2. Here delta x is lambda by directly we can put it in the equations. Delta x equals lambda by x, and formula of phase difference and path difference, delta phi equals 2 pi by lambda into delta x. So 2 pi by lambda into delta x. So delta x means lambda by 6. Lambda lambda get cancelled. 2 ones are 2 threes are. So phase difference is pi by 3. Substitute the value of phi in equation, that is I equals I naught cos square. That is phi means pi by 3. Here already 2 is there. Phi, that is pi by 6. that is pi by 6. Then I by I naught equals I by I naught cos square pi by 6, cos square pi by 6, I by I naught. See, cos pi by 6 means cos 30. Cos 30 means root 3 by 2 whole square. So I by I naught, root 3 by 2, nothing but root 3 means 3 divided by 2 means 2 square, that is 4. So what is the value of 3 by 4? What is the value of 3 by 4? That is 0.30, that is what 0.75. 0.75. So answer is option 4. Question number 9. The wavelength of light used in Young's double slit experiment is lambda. The intensity at a point on the screen where the path difference is lambda by 6. By using the path difference, we can calculate phase difference. Already we know that phase difference delta phi equals 2 pi by lambda into delta x. Substitute the value of phase difference, we get value of phase, that is pi by 3. Substitute this value in equation I equals I naught cos square pi by 6. Then question is, you can calculate I by I naught cos pi by 6, nothing but cos 30. Cos 30 value is root 3 by 2 whole square. So root 3 by 2, nothing but root 3 whole square, 3 divided by 2. So we can cancel 30 by 4, nothing but 0.75. So answer is 0.75. Is it clear? So next one. Next one. So next one. Question number 10. Question number 10. What is the minimum thickness of a thin film required for constructive interference in the reflected light from it? What is the minimum thickness? Given what is the minimum thickness, we have to calculate T, and required for constructive interference in the reflected light from it. Given refractive index of the film is, that is mu equals 1.5, and the wavelength of the incident light is lambda equals 600 nanometer, that is a nanometer, that is what -9 meter. Then what is the minimum thickness? So here the formula is 2 mu t, that is 2n plus 1 lambda by 2. 2 mu t equals 2n plus 1 lambda by 2. So next for minimum thickness, t equals how much? 0. Then minimum thickness, for minimum thickness, n is 0, not t. So we have to calculate minimum thickness only. So n is 0. This term is because that is 2 mu t, that is equals lambda by 2. Is it clear? Then 2 mu t equals lambda by 2. We have to calculate thickness, lambda divided by 2 to 4 mu. Lambda is 600. 600 into 10 to the power of -9. 4 mu means 4 into 1.5. So that is 600 into 10 to the power of -9. 1.5 into 4 is 6. That is 6 ones are 6 hundreds are. So answer is 100 nanometer. So note this formula. Note this formula. So 2 mu t, mu means thickness of the sheet, that is 2 mu t equals 2n plus 1 lambda by 2. So for minimum thickness, n is 0. Is it clear? So then answer is 100 nanometer. Option 1, 100 nanometer. Is it clear? Is it clear? Finish? Okay. So next one. Question number 11 is so question number 11, most and easiest question. Two monochromatic light waves of amplitude 3A. Amplitude is 3A and 2A. A1 is 3A and A2 is 2A. Interfering at a point have a phase difference of 60 degree. That is, they are given phase difference 60 degree. The intensity at that point will be proportional. Then we have to calculate only, we have to calculate intensity of the wave. So what is the formula? It's a direct formula. First we have to calculate amplitude. That is square root of A1 square plus A2 square plus 2 A1 A2 plus 5. 2 A1 A2 plus 5. Already we know that. So A equals square root of A1 square, that is 3A whole square plus A2 2A whole square and 2 A1 A2, that is 3A 2A cos 60. That is A equals 3A square nothing but 9A square plus 2A 4A square plus 3 2s are 6, 6 2s are 12 A square, that is cos 60 nothing but 1 by 2. So 2 1s are 2 6. A equals square root of 9A square, 9A square, 4A square plus 6A square. So 9A square plus 4A square, 13A square, 13A square plus 6A square, square root of 19A square. So A square, because squaring on both sides, 19A square. So, but this is resultant intensity, this is the amplitude value, but in the question, we can calculate intensity at that point. So already we know that what is the intensity formula? A is directly proportional to A square. That is I equals A square nothing but 19 A square. Clear? So option is, so answer is I equals 19 A square. Is it clear all of you? Note down. Next one is so next question. In the year 2011 KCET, in the 2011, consider following statement in case of Young's double slit experiment. Option A slit S is necessary if we use an ordinary extended source of light. A split S is not needed if you use an ordinary but well collimated beam of light. As 3, a split S is not needed if you use a spatially coherent sources of light. See, all these statements are correct. So option, which of the above statements are correct? So that is option 1, A, B and C. Is it clear? So next one, so just a theory type question. So next one, in Young's double slit experiment, question number 14. That is 2012 KCET question. In Young's double slit experiment, fringes of width beta are produced on a screen kept at a distance of 1 meter from the slit. Then what is the given data? That is capital D equals 1 meter. Is capital D equals 1 meter. From the slit. When the screen is moved away by 5 into 10 to the power of minus 2. Moved away, that is starting, if the slit and the screen is starting is 1 meter, if the screen is moved away by 5 into 10 to the power of minus 2. Away means what is the distance? That is delta D equals 5 into 10 to the power of minus 2 meter. Fringe width changes by that is also delta B equals 3 into 10 to the power of minus 5 meter. The separation between the splits is D equals 3 into, or is separation between the splits is 1 into 10 to the power of minus 3 meter. The wavelength of the light used in nanometer is. You have to calculate wavelength. See, what is the formula of wavelength? We have to calculate wavelength. So that is delta B equals lambda D divided by D. You have to calculate lambda. So delta B nothing but 3 into 10 to the power of minus 5. Lambda D. We have to calculate the lambda. Then what is the value of D? Delta D 5 into 10 to the power of minus 2 divided by small d 1 into 10 to the power of minus 3. So I need the value of lambda. So that is cross multiply 3 into 10 to the power of minus 5 into 10 to the power of minus 3, 10 to the power of minus 8 equals 5 into 10 to the power of minus 2 lambda. Is it clear? So then lambda equals 3 into 10 to the power of minus 8 divided by 5 into 10 to the power of minus 2. So we can shift 3 into 10 to the power of minus 2, that is 3 divided by 5. 3 divided by 5 into 10 to the power of minus 2, and if 10 to the power of minus 2 goes to numerator, that is plus 2, minus 8 plus 2, that is 10 to the power of minus 6. That is lambda equals 3 by 5, nothing but 0.6, 0. Nothing but 30, 30 by 5 divided by 5, 6 are 30, that is 10 to the power of minus 6. We have to shift the formula. See, keep in mind, if decimal point 10 to the power of plus, if point shifted right side, if 10 to the power of positive, for decimal point shifted right side, power decreases. If 10 to the power of negative, decimal point shifted right side, power increases. And if 10 to the power of power is positive, if shift decimal point left side, power increases. And here power decreases. So keep in mind. So this picture we clearly represent power decrease and increase. That is here decimal point shifted right side. Here 10 to the power of minus. Here 10 to the power of minus. If we shift the decimal point right side, power should be increases. Then 600 nanometer. 0.6 nothing but 600 into 10 to the power of minus 9, that is 600 nanometer. So option is that is 2, that is 600 nanometer. Is it clear? Note down. Most of the questions from Young's double slit experiment. So next one is question number. See, question number 15. For sustained interference fringes in Young's double slit experiment, essential conditions are in the last class. We had discussed about what is the condition for sustained interference pattern. What is the condition for clear interference pattern? Two waves must having same wavelength. Two waves must having constant phase difference. Two waves must having equal frequency. So, in the question number 15, in the year 2012, in the year 2012, for sustained interference pattern, sustained means clear, alternate bright, dark, bright, dark, bright, dark fringes, clear interference pattern. What are the essential conditions are? So, option A. So, statement A, sources must be coherent. The intensities of the two sources must be equal. So, statement B is wrong. Intensity of the two sources must be equal. It is statement wrong. But statement A, sources must be coherent. If two sources must be coherent, then we get a clear interference pattern or sustained interference pattern. So, here the correct option is both A and B. Wrong. Only A. That is correct. Option 2 is the correct. For sustained interference fringes in double slit experiment, essential conditions are, that is only A is the correct statement. Source must be coherent. Clear? Next one. We move on to the next one. So number 17. If the splits in Young's double slit experiment are of unequal width, in Young's double slit experiment, the split are unequal width, then option A, the bright fringes will have unequal spacing. See, in and the bright fringes will have unequal brightness. No, and the fringes do not appear. The dark fringes are not perfectly dark. See, if the splits in the Young's double slit experiment are of unequal width, means intensity is also unequal. If the splits are not unequal, intensity is not also unequal. That is I minimum, that is I1 minus I2. That is also not equal to 0. So intensity I minimum is also not equal to 0, means the dark fringes are not perfectly dark. Fringes do not appear. No, fringes always appear. If the splits in Young's double slit experiment are of unequal width, so intensity I minimum is also not equal to 0, then the dark fringes are not perfectly dark. So answer is option 4. Clear? Okay. I think all of you understood. I hope all of you understood what are the questions in the previous year. That is, the chapter name is wave optics. So next question is question number 19. Which of the following phenomena support the wave theory of light? So in the earlier, in this chapter, uh, what are the phenomena which proves wave theory of light, and what are the phenomena which proves particle nature of light? So already I told in the starting of the chapter, these are the phenomena which proves wave theory of light, and these are the phenomena which proves particle theory of light. So once again, I will repeat. What are the phenomena which proves wave theory of light? Wave theory of light. That is, first one is interference. Interference. Second one is diffraction. Diffraction. And third one is polarization. Third one is polarization. And what are the phenomena which proves particle nature of light? Particle nature. What are the phenomena which proves particle nature? First one is photoelectric effect. Photoelectric effect. Second one is scattering of light. Scattering of light. Third one is Compton effect. So now the question is, which of the following phenomena support wave theory of light? Option A, scattering. Is it correct? No. B, interference. Is it correct? Yes. Diffraction is also correct. And the velocity of light in denser medium is less than the velocity of light in rarer medium. So this is also correct. This is Huygens proofs. Huygens proof velocity of light in denser medium is less than the velocity of light in rarer medium. This also statement is correct. So a denser medium, that is option A is scattering, that is, which proves particle nature. So option B, C, D is the correct answer. So option 3 is the correct. Is it clear? Note down. What are the phenomena which proves wave theory of light? Interference, diffraction, and polarization. And what are the phenomena which proves particle nature of light? That is interference, scattering of light, photoelectric effect, and a Compton effect. Is it clear? So next one is, we move on to the next question. Next question. Next question. See here, polarization and polarization and diffraction problems are there. The next class we have discussed about different polarization and diffraction problems in the next class. Just today, I'm going to discuss with Young's double slit and interference problems. The next one is here in Young's question number 23. That is here in the year 2016 KCT. 2016 KCT. In Young's double slit experiment, the source is white light. In Young's double slit experiment, source is white light. White light. One slit is covered with red filter and other with the blue filter. There shall be. See, this is a Young's double slit experiment. In Young's double slit experiment, the source is white light. Here, this one is white light. And this one, experiment source, one slit is covered with red filter. One slit is covered with a red filter. And other with blue filter. And other with blue filter. Thus, there shall be alternate red and blue fringes, alternate dark and pink fringes, alternate dark and yellow fringes, no interference. See, that is interference formula, that is beta equals is lambda d by d. See, if two different wavelengths are, if two different, that is lambda red and that is lambda blue. If two different wavelengths are not considered in Young's double slit experiment, if what is the condition for sustained, what is the condition to get a sustained interference pattern? Two waves must having same wavelength. Here red wavelength is different, blue wavelength is different. Here there is no interference pattern. Here there is no interference pattern. So these are what are the conditions for sustained interference pattern? Already you know that. Already I told that is two waves must having same wavelength. Is it clear? So then option 4 is the right answer. No interference. Is it clear? So next one is, so next one is question number 26. Question number 26. According to Huygens principle, during refraction of light from air to denser medium. So in the starting introduction classes, I clearly told that wavelength and speed, nothing but when light passes from a rarer medium to denser medium, its speed decreases. It is here, already we know that speed decreases, here wavelength and speed increases. So option 1 is, and wavelength decreases but speed increases, wavelength and speed decreases, wavelength increases but speed decreases. So option 3 is the correct, both wavelength and speed decreases. That is because V equals f lambda. If speed decreases, wavelength is also decreases. Is it clear? So next, and the next one, in Young's double slit experiment, question number 29. Question number 29, that is 2018 KCET. See, most in Young's double slit experiment, most of the in the previous year, most of the questions from Young's double slit experiment only. So concentrate more questions on Young's double slit experiment and concentrate what are the formulas and what are the concept in Young's regarding Young's double slit experiment. So I hope all of you understood previous year problem. What I discussed in this class. Otherwise, next question number 29. In Young's double slit experiment, two wavelength, that is lambda 1 equals 780 nanometer and lambda 2 equals 520 nanometer. 520 nanometer and are used to obtain interference fringes. If nth bright band due to lambda 1, n bright band due to lambda 1 coincide with n plus 1, with n plus 1 bright band due to lambda 2, due to lambda 2, then the value of n is, then the value of n is n plus 1 lambda 2, then the value of n is, that is, we can continue the problem, that is n equals n plus 1, n by n plus 1 equals lambda 2 divided by lambda 1, lambda 2 divided by lambda 1, that is n divided by n plus 1, n divided by n plus 1, lambda 2, what is the value of lambda 2? 520 nanometer and 780 nanometer. See, nanometer, nanometer get cancelled. See, 1010 get cancelled. Then n by n plus 1 equals 52 divided by 780. That is 3 is divided by 4 is that is 15 52 divided by 78. 2 ones are, 2 twos are, that is 2 6 divided by 2 3s are 6, 2 9s are, that is 13 2s are divided by 13 3s are. Is it clear? Then n divided by n plus 1 equals 2 by 3. Cross multiply, 3n equals 2n plus 2. 3n minus 2n equals 2, that is n equals 2. Is n equals 2. In Young's double slit experiment, two wavelengths, that is lambda 1 780 nanometer and lambda 2 520 nanometer, are used to obtain interference fringes. If the nth bright fringe due to lambda 1 coincide, nothing but coincide with both lambda 1 lambda 1 is equals to n plus 1 lambda 2. So we can solve like this. We get n equals 2. So option is 3. Is it clear, all of you? Okay. So a few more Young's on the basis of Young's double slit experiment problems are there. We can solve. Then in the next class, we will discuss about diffraction and polarization synopsis and problems. Okay. See you in the next class. Thank you.